Swayam Prabha. Digital India. Educated India.
So I will supposed to take two classes today. The first one will be on why not use this color only? So hyperplane point duality. So Rajit Vishnu has already introduced point line duality in R2 and in R3 also, no? You did slightly? Between R2 and R3, okay. Yeah, so and also we will prove kind of a dual complex property. So before we do that, so let's slightly recollect some of the things we have done from yesterday. Oh, I'm sorry, yes. So the definitions that we saw, one was polytopes. Polytopes were convex hull of finite point set in RD. So okay, again we will be working in RD. Okay. Then we had this polyhedron, which are intersection of finite number of half spaces in RD, right? And we saw some, okay, we saw what is simplicial complex, and some basic results on these things. Okay. On this topic. Okay, so before I begin today's class, I need one more definition, what are called cell complexes. Okay, so cell complexes will be generalization of geometric simplicial complexes. Okay, so what will it be? So it will be collection of polyhedra in RD satisfying the following properties. So the properties will be very similar to the simplicial complex construct. Oh, okay. Is it okay? Following. Sometimes your handwriting is so bad, doesn't matter how big you write. Huh? I may be suffering from that ailment. Okay. Yeah. Following. So it will be similar to what we saw for geometric simplicial complexes. Okay. So the polyhedras that will be contained in the set, we will loosely call them faces. Okay. So it will have this property. It will be like face of a face in the cell complex is also in the cell complex. So this is not a tongue twister anyway. What does it mean is what we had for simplicial complexes. If a simplex is present, always faces are present. Okay. The second thing is intersection of two faces is also a face in the set, in the cell complex. Okay. Cell complexes doesn't have to be union of the polyhedrons doesn't have to be convex sets, by the way. Okay. So like simplicial complexes doesn't have to be convex sets, right? We saw the graph is a simplicial complex, right? Also in the same way we define dimension, you can define dimension here also. So I won't define it, but you can define dimension of cell complex also. Okay. Yeah, so let me give one example that we will mainly be working with. So the main example that we will be working with for cell complex in this class and the next class also is what we will be looking at is we will have a polyhedron, okay, and we will be looking at the faces of the polyhedron. So you have some polyhedron P, okay. Pardon?
Cell complexes. Can you explain it?
Bit more again? Okay. Yeah. So, sure. So you remember what was the definition of a polyhedron was, right? I mean, it is intersection of finite number of half spaces. So now, oh by the way, so a polyhedron in let's say RD, okay, is it always the case that it should have dimension D? So remember what was the dimension? I think we defined the dimension last class also. The dimension of a polyhedron was the minimum affine space, dimension of the minimum affine space that contains the polyhedron, right? So does it always have to be D? It can be smaller. Can you give an example? Pardon? Sphere? No. Oh, you mean like combinatorial sphere? You mean that? Okay, whatever. So okay, so let's like an hyperplane. Okay, so let's look at this. So I will just recollect this and then. Okay, so let me remove this. So explain with some examples then. So other examples. So one is, what about hyperplanes? One hyperplane. Is it a polyhedron? So hyperplane H, okay, which is something like nothing but all the x's satisfying hx equals to 0, where hx is a affine function, linear function. So hs is of the form some ax plus b equal to 0, b belongs to R, a belongs to Rd. Is it a polyhedron? Yes, no, no, no. So, but see, look at H is nothing but intersection of H greater than equal to 0 and H less than equal to 0. Right? So it is a polyhedron. So it doesn't have to be like a polyhedron in RD in general doesn't have to be a d-dimensional objects. Okay, it can be lower dimensional objects also. Okay. So again, let's go back to the definition of cell complexes. So we have a collection of polyhedrons in RD. Okay. Similar to simplicial complex, we have a collection of simplices in RD. What was the property for simplicial complex? Geometric simplicial complex. What we wanted was a face of a simplicial complex should also be part of the collection. Same here. A face of a polyhedron is a polyhedron itself, okay, another polyhedron, okay, that polyhedron should be part of the collection also. Okay. The second thing is intersection of two polyhedrons, okay, should also be a polyhedron in your set. Okay. Yeah, sure. So let's say you have an object like this. Let's say you have in my collection I have this box 1. So interior is also present, and I have a box 2. Interior is present. They are intersecting in this region. Okay. What I have done is in my collection I have included the vertices of box B1. The box is present, the vertices are present, the edges are present. Okay. Similarly for B2 also, the vertices are present, edges are present, and the box B1 is also present. Is this collection a cell complex? See, it is not, because the intersection is not in your collection. Okay. So, let us say a polyhedron itself, okay, just one polyhedron. Okay. My set includes just, so this is one example, look, let us look at example 2. I have just one polyhedron, okay, and let us say it has faces. Okay. So, is this polyhedron, is this collection a cell complex? It is not, because the subfaces are not included, you have to include the subfaces. Similarly, we did it for simplices, right. So, I mean the example to take is basically if you have if you just put one simplex, okay, will that form a simplicial complex? Okay, if the simplex is a vertex, okay, it is forming, but other than that, even if it is an edge, a triangle or whatever, okay, just this a collection that just include one simplex won't be a simplicial complex. You have to make sure all the faces are present. Okay.
So one is contained within other, then it will be a cell complex.
But
Suppose here B1 the box B1 and intersection B2, the face is not within this, so that is not a cell. So if B1 is within B2, then
B1, pardon?
B1 is within B2.
Oh, then that is okay. As that's the, by construction I said I included B1, B2 and all its faces in the set. Yeah, that's okay. That's perfectly fine. Is it clear now? Definition, okay. Think of what we had for simplicial complexes. We have replaced simplices with polyhedron. Okay. Good. So, we need another concept, what is called dual complex. Okay. Let us say let K and K prime be d-dimensional cell complexes. Okay. Okay, I will say K and K prime are dual complexes if there is a bijection between K and K prime such that I want is if, so let us say the bijection is pi, okay, bijection pi, okay, such that if K sigma belongs to, let me not write sigma, what should I write? So, sigma here is a polyhedron, okay, sigma belongs to K is t dimensional, then pi sigma should be d minus t dimensional. It sounds kind of an odd, no? There's a dual complex and so on. But it's kind of also like not that odd. You have seen one example. Two examples in this course, two structures that were introduced in this course, which are dual complex of each other actually. I guess. Pardon? Can you come again? No, abstract and geometry, they are exactly isomorphic, right? K takes to K, right? Okay, so exactly example. Okay, the main best example will be that is the one we will anyway will be working with most of the time today. A Voronoi diagram, okay, and the corresponding Delaunay triangulation. So let's not call it triangulation. I like to call it Delaunay complexes. All I mean, like for any given point set, a triangulation may not exist. You need a general position as assumption. Okay. So, so you have the Voronoi diagram. Voronoi diagram is, by the way, a cell complex. Okay, but you have to define it properly then. How should you define it? So let's say I say, so you have a point P, point set P with points P1. So let's do it in R2. I mean, goes through in RD. Okay, so and let's say they are in general position and whatever. Okay, so let's do it in RD itself. So why not? Okay, so this is a subset of RD. Okay, so we defined a Voronoi cell of Pi to be all the x's such that distance between x comma Pi is less than equal to d of x comma Pj. Firstly, is this a first question is this a polyhedron? Yes, exactly. So this is a polyhedron. How do you find it? Take any Pj, find the half plane, find the plane that bisects the segment Pi Pj, take the half plane that contains with respect to this hyperplane that contains Pi, right? Do it for all Pj and take their intersection, right? So you get Vor of Pi. Okay, so that is a polyhedron. Good. Is intersection of n half spaces. Okay. But now let's say make a collection. I call it K to be Vor of Pi. That's it. For all I belonging to. Is this a cell complex? Is this a cell complex? I mean, from the tone of my voice, you should guess. Even if you don't know the answer, it should be no, right? I mean, there should be something more. Why should there be something more? So let's take P1, P2. Okay, let's say their Voronoi cells intersect. Let's take in terms of R2. So either it will intersect at some vertex of their polyhedrons of the Voronoi cells or an edge. But are those included in this set? I have only included the two-dimensional objects for the case of R2 here. And if I think of d is equal to 2, I have only included the two-dimensional objects. Okay, you should make sure you include all the lower dimensional objects also. Okay, but if you do that, so one thing you can do is first you get the Voronoi cell and then include all its faces. Okay, add VAPI and include all its phases. For each Pi, okay, that will be a valid one, right? Good. But when I include these phases, what am I really? Do they have any value? Right? Let's say I took a simplex, I add all its phases. Okay, why did I do it? I did it because I wanted to make a simplicial complex out of it. Okay, but when I do this, am I doing it like the new faces that I have introduced? Do they contain some interesting property? So let's say Voronoi of P1 intersection Voronoi of P2. Okay, this polyhedron, what does it say, does it have some interesting property, like points contained in this polyhedron? What is the interesting property that it has, the points in this polyhedron? This includes those points that are equidistant from Pi, P1, P2. Okay. Similarly, all the faces that I have included, actually they encode these Okay. So, any phase that I have included, so any phase sigma that I included in K. Okay. So, let me write. So, when we define Voronoi Vor of capital P, I mean all the Voronoi cells of vertices and its faces. I have included all the faces in this set also. Okay. So, this is a set. Abuse of notation I am just purposely. Okay. But these each phase, what do they store? Each phase will there will exist for each phase sigma, there will exist some P1 to Pt in capital P such that var Pi intersection I equal to 1 to T will be equal to sigma. Okay. Good. Now, let us look at the definition of the Delaunay complex. So, Delaunay complex, if we define, so how did we define? It was nerve of like the set var Pi, right, this I equal to 1 to n, right. Since this was a nerve, it was a simplicial complex, right, nothing to worry about, do not have to make it a simplicial complex, definitionally it is a simplicial complex, okay, because nerve of any collection of sets is a simplicial complex. Okay. Are they dual to each other? Okay. This is something we will be studying today. Okay. This is something we will look at today. Pardon? Can you come again? So, let us take a Voronoi, let us take a phase in var P, var capital P. You remember var capital P not only includes var Pi's, but all its subphases also. Okay. And I am saying is each subphase corresponds to each x in subphase corresponds to points that are equidistant from some set of points in P. That is what there is a one-to-one connection. Okay. Now, why did I say Delaunay complex? The way we have defined Delaunay complex. So, let me give you one example and then we will look at, so these things we will do in next class, but let us look at the Delaunay complex, and when I say it is not a complex that is, you can always draw in the plane. So, let us say in R2 itself, there may be a problem. Okay. So, let us take 4 points on a unit square. Okay. Your P set P is, capital P is P1, P2, P3, P4, okay, and they are on this unit square. Okay. How does the Voronoi diagram look? So, let us say for P1, P4 I am drawing, or let us say P1, it will look something like this for P1. Okay. Similarly for P2. This will be the region for P2, this will be the region for P1, P4, right. So, what are the simplices that are, so what will be the corresponding Delaunay simplices? Firstly, we will have the points P1, P2, P3. So, I am purposefully writing it as a set, okay, because the way I said it does not have to be, the Voronoi complex is a combinatorial, like it is a abstract complex. Okay. Then you have P1, P2, there is a non-empty thing, right. Voronoi cell of P1 and P2 are intersecting. So, we will have P1, P2, P2, P3, P1, P4, all of them, right. Then you will have these triangles. This triangle will be present because this point belongs to both P2, P3, Voronoi cell of P2, P3 and P4. Similarly, all the 4 triangles, okay, you can make with this 4. Okay. Also, you will have one size 4 set P1, P2, P3, P4. Okay. Right. See, this will be, I mean, whatever be the embedding, straight line embedding of this complex, Delaunay complex, you can have an embedding, right? We know in R, like if the maximum dimension is T, we know I can embed in R2 T plus 1. Okay. So, this can be embedded in dimension 7, R7. But one thing we know, it cannot be embedded in R2, by the way. Can I embed it in R2? See, to embed it in R2, I need to find points corresponding to P1, P2, P3, P4 that will be affinely independent. Can 4 points be affinely independent in R2? Okay. So, this complex cannot be embedded in R2. Yeah. Is this is this set P1, P2, P3, P4 in general position? See, the way we defined general position was any D plus 1 in RD, any D plus any sets of size less than or equal to D plus 1 should be affinely independent. This is true, by the way, here. They are affinely independent. We need something more to make Delaunay complex embeddable with the same point set. We need another condition which is called general position with respect to spheres, or for in R2 general condition with respect to circles. So, I will say a point set P is in general position if that D plus 1 property holds in RD, and there does not exist a sphere S in RD that contains greater than equal to D plus 2 points, not greater than equal to, yeah, okay, that's it, D plus 2 points of P. So, in R2 it will be, there should not be a circle that contains 4 points. Okay. There is a circle that contains these 4 points. Okay. So, one of the goal of this 2 lectures will be to show if the general position assumption is true, both in terms of affine independence and in terms of spheres, then the Delaunay complex is embeddable in RD with the same point set. Not only that, it triangulates the convex hull. Okay. What do you mean by triangulates the convex hull? It is a simplicial complex, okay, that covers the convex hull. Convex hull of P. Okay. So, this is what we want to show. Okay. Okay, so, let us now go to, okay, I have half an hour at least. So, now let us look at point hyperplane duality. Okay, so, let us again look at, let us go back to RD. Okay. You can define so let me see. So, you can define paraboloids. So, paraboloid in RD of the following form. Paraboloid, let us say, call it, this will be a fixed paraboloid, following form. Okay. These are, Q will be all those x such that, so okay, by the way, I will, so for any x in RD, I will represent the corresponding coordinates as x1, x2, small x1. Okay. And I maybe, because I am using points for it also, no, so there is suffix, So, let me write it like this. So, x of 1, x of 2, see the first coordinate, second coordinate, third coordinate, I will represent like this, okay, because I am using suffix for points. Okay, so all those x's such that x of d is equal to summation I equal to 1 to d minus 1 xi square. It's a parabola that goes through the origin. Okay, this looks like this, right? If I will have to draw, you can think of this axis is xd, the paraboloid, and this is the origin, so it looks like this. Okay, this is basically r of d minus 1. So I am associating the first d minus 1 coordinate with r d minus 1, right? It looks like this. Is it okay? So let's take a point P in the paraboloid. Okay. So we will denote by P star tangent to the paraboloid to Q at P. Okay. This is something Arijit Vishnu derived, right? So what will be the equation of P star? All those x which satisfy the following equation. I mean, you can derive, I am just writing the simplified one, derive it in a slightly different, but this is the simplified form we will be using, and there is a reason I want to write it like this also. Okay. Is it okay? This is tangent. Everyone like vaguely understand what is a tangent to, let's say, a curve or a surface, right? Okay, good. When it like this is a hyperplane that touches the surface at that point. Okay. Okay. So now we want to build a framework for points and hyperplanes in RD. Okay. So what do I want to do? I want a mapping. So if I given a point in RD, I want to take it to a hyperplane. Okay. This is something we want to do. Okay. So, and I want to do it in such a way, whatever be your definition, I want to do it in such a way that P, if the point is lying on the paraboloid, the dual hyperplane should be the tangent to the paraboloid at P. So, should be P star. Okay. So, the definition should be such, if P belongs to Q, then the dual thing that you are defining, let me write it as D of, let me dual of P, let us say, dual of P, which will be a hyperplane in RD, that should be equal to P star. That is how we want to define. So, you make this connection. So, okay, one more thing. So, okay, so we want to make this connection. We won't be looking at all hyperplanes also in RD. We will be looking at hyperplanes that are non-vertical. So what do I mean by that? Non-vertical means the equation of the hyperplane be such that the coefficient corresponding to xd should be non-zero. So what do I want to do? I want to take points in RD to hyperplanes in RD which are non-vertical. What are non-vertical hyperplanes? Hyperplanes whose coefficient, see, hyperplane will be a solution to a linear equation, right? So whose coefficient of xd should be non-zero. Okay. So how do we do this? So let's say Q be another point in RD. It doesn't have to be on the paraboloid. Okay. Its dual Q star. Okay, this is a dual. See, this is not the tangent at Q. Q doesn't have to be in the paraboloid. I just want to abuse this notation as much as possible and confuse you as much as possible also. same time, is all those x such that xd minus 2 times qi xi I equal to 1 to d minus 1 plus qd is equal to 0. Okay. So, q goes to q star, but it is a duality. I have already restricted my set to all the hyperplanes that are non-vertical. So, coefficient. So, assume you have written the equation of non-vertical hyperplanes to be such that the coefficient of xd is 1. This we always can do, right? And divide that by the coefficient, whatever. If the coefficient is some number, divide it by that coefficient. Okay, it becomes 1 equation. Okay. So, I have to get a map from here to here also. So, if I take a hyperplane H, I want a point H star in at D. So, let us say the equation of the hyperplane was all those x such that xd plus summation, I am just writing it as an equation like this. So, h1, so let me write as a coefficient, okay, why not, okay. Coefficient ci xi I equal to 1 to d minus 1 plus cd equal to 0. How should I define H star? H star should be defined in this way. So, it will be, the first will be, so let me as a H star of I will be minus of Ci by 2 for all I less than equal to d minus 1. Okay, and H star of D will be CD. Okay. So, for those who wants to see it as a vector, it will be like H C1 by 2, C2 by 2 minus C of D minus 1 by 2 comma CD. It's okay? Okay. Let me keep it here. Okay. So, once you define duality like this, it has an interesting property. This is what is called bijective involution. This is okay. So, what does that mean? So, don't have to know these terms, but what does that mean? So, if I take a hyperplane, pardon? Here, H star I will be this. So, this is, see, I am defining it, right. So, there I want to define a duality between points and non-vertical hyperplanes. And non-vertical hyperplanes written in a particular form also, I want to write it. See, first I have to define what I mean by duality. So, one duality is like I am taking points to hyperplanes, hyperplanes to point. This is happening, but I want this duality to satisfy some more properties, and you will see what are those properties this satisfy. Okay. So, from now on, whenever I am talking about non-vertical hyperplanes, I will be always be writing them in the following form, that xd with the coefficient of xd being 1. Okay. So, whenever I say H is a non-vertical hyperplane, and when I define H plus H minus, you know that write it like this and then define H plus and H minus. Okay. The equation should be written like this, and for with this form, this way, once you written it like this, then you define H plus and H minus. By the way, one more thing, just as a picture thing. So the hyperplanes will be like this, right? I mean, non-vertical ones. Okay. H star will be like this side. the way we have defined it, since we have taken the coefficient of xd to be 1, okay, that means when I put xd equal to infinity, you should get positive value. Keep everything 0, hd equal to infinity, then you should get a positive value. It goes to infinity, right? So, once if you have written the equation of non-vertical hyperplanes like this is how it decomposes the space, okay, at D. And you will see why this will be useful. The theorem we will be proving now, but let us prove some simple things about this. So, let us start with a non-vertical hyperplane, okay. We start with this, I do the dual, I get H star, I get a point, this is a point in RD, I take dual again, H star star, again I will get a non-vertical hyperplane, but it has a nice property, H star star is nothing but H. Similarly, so let me call this properties. So, one is this. Second is, now I start with a point, I take again dual, I get P star, which is a hyperplane, non-vertical hyperplane, and then I again take P star star, I get a point back. This is again a point in RD. What is the property? It is P. Verify this equation. This is the way we have defined. It works out like this. Good. Something even more interesting happens, okay, which is, let us say P belongs to H. Then H star belongs to P star. This is a point, take the dual, you will get a non-vertical hyperplane again, right? And what I am saying is P star star, which is the dual of P star, will be equal to P. The way we have defined it, if you work out the, oh okay, I am sorry, it looks phi, is it? Okay, I am sorry, thank you, it's P. Okay. Yeah, it's a very subtle, when I write pi, this should be like this. I am joking, I write it in a bad way most of the time, so it should be written like this, empty set anyway. Okay, so this is one property also. So what does it say? This is called preserves incidences. So think of it in terms of points and lines, the way we have defined incidences, right? So let us say P lies on L, then what does this say? L star will lie on P star. Okay. Property 4. This goes in, this goes in the other direction also, but what to prove here? I have already proved star star is thing. Okay. So the fourth thing, let's do this. Call it. Let's say P belongs to H plus. Then what do we expect? H star should belong to P star plus. Same with minus. So, preserves the sides. Pardon? Can you come again? No, yeah. So just on. So we have this, right? This is, as we said, this is a. So let's say this is XD. So this side for any hyperplane H, non-vertical, this will be H plus, right? The top side. Okay. The way we always write the equation, as I said, XD, coefficient of XD to be 1. It's important to put the coefficient of XD to be 1. I mean, the preserving side you can still preserve it with different ways, but for this 2 talks, I want to maintain this notation. Okay. Yeah, so this will become clear when we do prove some results. Okay, let me see if I wanted to say something more. Yeah, that's it. Okay, so let's do let's look at this case. Let's say P be again set of points in RD. Okay, so I can make a convex hull of P. Right. I can also define what is called lower hull of P. Assume this is in general position. By general position here, I mean just affine general position. Okay, no D plus 1 point. Any subset of size less than equal to D plus 1 will be affinely independent. Okay. So, I want to define lower hull of P. This will be a subset of convex hull of P. Okay. So, how, pardon? So, take any D plus 1 points, they will be affinely independent. So, assume n is larger than D plus 1. So, if n is larger than D plus 1, you do not have to say any subset of size less than equal to D plus 1. You say all the D plus 1 are affinely independent, you are done. Okay. But verify this. Okay. These are very easy to check, but verify. Okay. So, I want to define what is the lower hull of this convex hull of P. Okay. So, how do we define it? So, let us say let H of P denote supporting hyperplanes of P. From that set, I take out H plus P denotes, which will be a subset of HP, will be non-vertical supporting hyperplanes of P. Okay. We define lower hull to be lower hull. So, remember, whenever I say non-vertical, that equation is written in that form. The XD is 1, coefficient of XD is 1. Lower hull is convex hull of P, whole intersection, all so let me write write like this, H belonging to H plus P, okay, H. Just 1 second, I made a mistake somewhere. Yeah. No, so just 1 second, I made a mistake here somewhere. Let me check. Okay, so yeah, so lower hull I will define it as a, it's not a convex body, no, so this will be a yeah, my mistake. H intersection convex hull of P, such that H belongs to H plus P. So here also it's not completely correct. Is in all will be H plus will be all non-vertical supporting hyperplanes of P, such that H belongs to H star of P if H greater than equal to 0, okay, contains convex hull of P. Okay. So let me, yeah, so I should have written the definition properly. So let's intuitively see what should be the definition, and then, so let's say I have a point set whose convex hull looks like this. And there are many other points inside, don't care. This is, let's say, XD. Okay. When I mean lower hull, I want these simplices, these vertices. Okay. So what am I including in H plus of P? H plus of P will be all those non-vertical hyperplanes whose non-negative side includes the convex hull. See, this edge, blue edge, will be supported on this non-vertical hyperplane, right? Its non-negative side includes the convex hull. Similarly, this is this. For this, you have this. For this, you have this. Even for edge, this vertices, you can also have it, right? You can have a hyperplane like this, touches at this point. It is supporting, and the positive side of this contains the convex hull. So these are the faces I have included in the lower hull of P. So lower hull of P will be collection of faces of the convex hull of P which satisfies this property. Okay. Now one thing, so let's say I have assumed that the point set P is in general position, right? A fine general position. What can we say about this? This will be polyhedrons, right? H is a face. H intersection convex hull of V will be a face of a polyhedron. It will be a polyhedron, like it's a polytope, even like polyhedron, polytope it will be, right? So with this, for this polytope, okay, is it a simplex or not a simplex? If P is in general position. So go back to the convex hull of P itself. Okay, I'm interested in the proper faces of convex hull of P. Okay, not the convex hull but the faces, lower dimension faces. Dimension from d minus 1 to 0. Okay. Since I am assumed that the point set P is in general position, what can I say about the proper faces of the convex hull of P? They will be simplices. This is something we discussed last class, right? So these things that we have, got H intersection these will be simplices. It's a simplicial complex, right? So lower hull of P will be a simplicial complex because P is in general position. Anyway, the faces, all the proper faces of convex hull of P itself, if I only make a set with these objects, it will be a simplicial complex. Okay, lower hull of P will be a simplicial complex which is a subset of this simplicial complex that we get by taking all the proper faces of the convex hull of P. This is happening because the point set P is in general position. Okay. So since we discuss for convex hull of points, so let us look at again a set of non-vertical. Let H be a set of non-vertical hyperplanes in RD. Okay. Again, they are written in the form xd coefficient is 1, which I can always do. Okay. You can define what is called the lower, like what is called the term, I keep forgetting the term. It's called upper envelope of the positive half spaces of H1 to Hn. So what do I mean by that? So let's make a polyhedron P in the following way. Let's call it P prime. Okay. So it will be intersection of Hi's greater than equal to 0, I equal to 1 to n. So it will look like what? So you will have this non-vertical hyperplanes, their positive side is this, and I have taken their intersection. XD is in this direction. Sorry. Right? I will get something like this. For this object, I can define also something called upper hull. Upper hull will be basically, I want this thing, these polyhedrons. It's okay. This is faces, right? This will be the faces of this polyhedron. Okay. One thing about this polyhedron, can this polyhedron be bounded? Pardon? Bounded from this side. From the top side will be unbounded, right? Because as I said, xd take larger and larger values, all the equations will start satisfying. Basically xd infinity is contained inside this, right? Polyhedron. Okay. Yep. So now with this object, this red thing is called upper envelope. What we will be doing is basically, given a set of points P, this is what we will be proving now. I can define, we have already defined what is a lower hull of P. It is a simplicial complex. Okay. So let me write as U to be like U of H to be this upper envelope. Okay. So what we will be showing is this lower hull and upper envelope of capital P star. So what do I mean by capital P star? I mean P star is set of hyperplanes P1 star, P2 star, Pn star. This sets upper envelope, and we will show this is these two objects are dual complex. See, the terms are different. Okay, so this is this definition is an envelope and it is a hull. Okay, and it is defined for slightly different objects also. Okay, you will see why I call it actually an upper envelope. Okay, it is a maximizer of a collection of functions, linear functions. Okay, we will do it in the next class, the way when we define Voronoi. Here I want to stay in this combinatorial framework. Okay. So what we are doing here, think of it as you have a collection of non-vertical hyperplanes. Okay. Now you look at their upward. You look at their, so it is H1 to Hn, and you are looking at intersection of Hi greater than equal to 0 for all of these hyperplanes. I get some kind of polyhedron. This is upward open. Okay, and I am interested in the proper faces of that polyhedron. Okay, I have defined what is the lower hull, which is again I am assuming P is in general position. Okay, just to make our lives simpler, you can do it for more general case also, but let us say P is in general position. So it will be anyway the proper faces of the convex hull was a simple shell complex. Lower hull is a particular the simple shell complex that lies like lower side of this convex. Which subset of which? No, doesn't have to be. No. See, this is for. So even okay. So this is easy to see even if you just draw it in R2. Let's say. Okay. So let's do it in R2 and see what is happening. So let's say in R2 I have defined like put x2 in this direction. This is x1. Okay. You have this quadratic, right? So let's say I take 2 points. What is the lower hull? Lower hull. Okay. Okay. What will it be? Its upper envelope. For this point, I have to take its dual, but I know that will be the tangent at this point only. So it will be something like this. So the object will be this and this. Firstly, even this is even like an unbounded object, right? Oh, I should draw it properly. So yeah. So I have taken 2 points, P1, P2 on the quadratic, right? Okay. And so what will be their lower envelope? So let's take, I mean, you say, okay, no, take one more point. Okay, so let's me. I took like P3. Yeah. So the convex hull is basically this. What is their corresponding lower hull? Lower hull is this. But the upper envelope you will get by taking, first you have to build like this polyhedron by intersecting it with this 2 half spaces. So which is basically all the points inside this cone. Okay. Then you are taking its 2 faces, right. So let me draw without this, just the upper envelope. The upper envelope will basically look like something like this. Oh yeah, I should have done a tangent. Yeah, should be like this then. Thank you. Yeah. This pink thing is a cell complex, and some of the polyhedrons are like unbounded, right. This one and this one are unbounded. So you get it, these two are different things, and it is not obvious why they should be dual of each other. It needs a proof. Okay. Okay, so theorem that we want to prove is, so lower hull of P is dual of upper hull of upper envelope of P star. So am I out of time or? It will take something. So I will do it after. So I will take the tutorial. So I will make tutorial a class. Okay. So I will have one class in the end also. So I have 2 classes after this. So I will take, yeah. So this is the end. If you have some questions, so let's get this clear because I will be start proving things now. Okay. But you get it now. These 2 objects are different objects. It is not even an isomorphic object. They're dual. Dual objects are also quite nice. These are dual. Once we have this duality theorem in place with an upper envelope and a lower hull, what you can do is you will be able to prove the duality theorem between Voronoi diagrams and Dillon triangulation. The proof actually is not different, but like you have to write few steps. So any question? Everyone got everything? That's perfectly fine.